All right, this is our last video related to the transformations of functions and their graphs. So in this video, we're going to use what we've learned to look at a graph and then write its equation. So this is going to require us to remember all of our parent functions, their basic shapes and their traditional points, along with all of our rules for transformations. So the first thing we're going to do the same thing we've been doing. We're going to identify the parent function. We're going to identify the transformations that have been made, and then we will put it all together. We're going to figure out how to do that graph. The first thing I want to do, let's look at this first one, is identify the parent function. And if we look at this, the parent function is the square root function, square root of x. So that's what we're dealing with. But of course, the square root would start at the point 0, 0, and we can see that this one is starting at the point 1, 2. So what that tells us is we have some transformations. And if we think about how we've moved to get this to this point, we've had to have gone to the right by 1, and we had to have gone up by 2. Now, I have not put these in the correct order because right now I'm just trying to get some information down on paper. So I haven't actually listed these in the correct order. I'm just trying to get ideas down. From here, we can see that it's clearly not pointing the same direction it should, right? So there's been a reflection. It's supposed to have gone from the initial point up, and it's gone down. So that tells us it must have reflected about the x-axis at some point. Reflection over x-axis. And then the last thing I need to do is make sure there aren't any sort of compressions or stretches. And so I'm going to look from that first point, and I know that the square root typically starts at 0, 0, and it goes up 1 over 1 to 1, 1. So I should see that if I were to go down by a full 1, I'd go over by a full 1. That looks exactly like what is happening here. Even though it's going down, that's because of that reflection. It is traveling on that over 1, up 1 pathway that we would expect. And I'm not going to try and trick you. I'm not going to make it something like 1.9 down 1 and over 1.9. So you can round these things. If it looks like it's maybe 1.8 or 1.9, just go around it. It does not appear that we have any reflections or stretches here, and we do not. So now I'm going to assemble this thing, and here's where I have to think about the order a little bit. The first thing that always has to occur is that right by 1, but now we're kind of deconstructing it, really. We're going backwards. So we need to make sure that as we're writing our equation, we're not going to mess anything up. Y is equal to, we always need to have the equation. It is an equation, so it needs to be y is equal to, or f of x is equal to, whatever we want to name it. It is a square root function, but we're doing some things to that x. If we want our function to go right by 1, we'd have to use an x minus 1. Remember, we always do the opposite. If we want to go up by 2, we would put a plus 2 out there. And then a reflection over the x-axis would mean we'd have a negative in front of the parent function. So this should be it, except for the fact we ignored order. That up 2 really should occur last, and that is fine, because we would do the reflection first. We'd have our parent function, we would shift it to the right, we would reflect it downward, and then we'd shift it up. So that is actually perfect. It's much easier to handle the up and down with reflections rather than left and the right, because the left and right is always applied first, and then potentially it moves in the wrong direction. We'll see an example where I talk about that in just a minute. Let's move on to the next one. The second one, number 2 here. Number 2, parent function here, definitely the x squared function. Next thing I'm going to think about are the transformations that have been applied. So it's not shifted left or right at all. It simply has gone down by 3. I'm not writing these in the correct order. I'm just writing them in the order that I see them, or that I can determine them. Now, it does not appear to have a reflection. Now, keep in mind we can always reflect a quadratic about the y-axis, and it doesn't change it as long as we haven't shifted it left or right at all. So I could put a reflection on there, but why bother, right? That seems unnecessary. I can write negative x squared, but x squared is just a lot easier to write, so I'm not going to worry about that. But I do need to check to make sure that there are no stretches or compressions. So typically with the x squared, we would go up 1 and we'd go over 1, but actually here, if we go up 1, we're not to the edge of the graph yet. So let's look at where that is. If we go over by 1 unit, we've actually gone up by 2 units. All right, so from our vertex, traveling over by a full unit, we go up by 2. And so what that means is we have vertically stretched this by 2. If I were to figure out the horizontal. I could also view it in terms of horizontal because remember we said that we can always view these things in terms of vertical stretches or horizontal compressions. We could do that, but to me it is much easier to view it in terms of that vertical motion. Right? That is always easier. And so what I'm looking to see is if I go over by the one that I expect, how far up have I gone? And I've gone up by 2, so that gives me that vertical stretch by 2. So now I don't see anything else. There's no other reflections or nothing else going on here. So I'm going to put it into my equation. Y is equal to, I have an x squared function. We said that we need it to go down by 3, so that's minus 3. Vertical stretch by 2 means we'd have a 2 in front of the x squared. We would not have it in parentheses. That would be wrong. So the 2 is in front of the x squared. If we think about the order, again, we had the order wrong. Really, the down should always occur last. But that's fine because we've ignored that. We ignored that when we looked at the shift. The first thing we'd do here is we'd start out, we'd say, well, let's stretch it up by 2, so it's gotten taller. And then we would shift everything down by 3. So that's perfect. That is our graph. And then the last one here, number 3. So the last one, this is definitely a x cubed function. That is our parent function. I can see that where it's bending around is not at 0, 0 anymore. So let's think about how we've traveled to get to this position. We've had to have gone to the right by 1. And we had to go down by 2. If I were to look at the stretches or compressions, I'm saying, well, if I go over by 1, have I gone down by 1? And yeah, that, again, it looks like an approximate here, approximately ballparking it with my eye. It looks pretty much, I'm not trying to trick you. We'll go ahead and call it 1. So there's no vertical stretches or compressions. But there's definitely been a reflection. This thing is facing the wrong way. Remember, x cubed normally looks like this. It's going the wrong way. Now, there are actually 2 ways I could reflect this pretty easily. I could view this in terms of a reflection over the x, because if it initially looked like this when we went to reflect over the x, it switches, that would be fine. Or we could view it as a reflection about the y-axis, because that would make this jump over here and we get to that same kind of backwards curve. And so I do have an option here. We have a reflection. The over is up to us. What I was saying before on this number 1, it was much easier to deal with the reflection when it was over that x-axis, because then it doesn't affect whether I'm going left or right. If I view it as a reflection over the y-axis, well, then I actually have to do the opposite thing at the outset on my left or right. Now, on the first one, there's only one reflection we could do. So sometimes we don't have this option of one or the other. Obviously, reflecting over the x-axis on the x squared is different than if we had instead reflected over the y-axis. It would be pointing completely opposite directions. But here, because we do have the choice, it would be easier to say it's a reflection over the x-axis. So let's write up that equation first. We'd have y is equal to, we have our negative inside with our, try that again, we have our negative on the outside of the x cubed. Because it's gone to the right by 1, we have the minus 1 inside of our parentheses. The reflection over the x means it's outside. The minus 1 would give us a right by 1. And then down 2, we'd have a minus 2. And this would work. This would be a valid equation. But let's say instead we had tried to say this is actually a reflection over the y-axis. Let's see how that changes it. Well, we'd say y is equal to, now we have to put the negative with the x. Let me stick that minus 1 there for just a second and leave everything else. So if I were to take this equation and dissect it, the first thing I would say is we do go right by 1. That would be true. Then we would have to reflect over the y. And then we would go down by 2. Well, let's draw it. First thing, right by 1. That would be our ballpark sketch. Next thing, we would reflect over the y-axis. Let's try that better. Let's finish that off. So we'd have our, there, that looks better. That would be our right by 1. Next, we would reflect over the y-axis. So this point jumps over here. Now, the direction of the curve is going to be fine, but notice we're on the complete wrong side of the y-axis now. Because those horizontal shifts always come first, they get messed up when we try and add in other applications or other transformations. So what I need to do to fix this is to put a plus right here. And that fixes my equation. This would now be a true equation. We would actually be going to the left first. We would then reflect back across, so then we are back in the right spot, and then we'd be going down by 2. So that would actually fix our graph. So we do have an option here. Which one was easier? I think definitely the first one. It is always easier to avoid reflecting over the y-axis, especially when we have a shift left or right. Is that always an option? No, it's not. So we can look at it and fix it. What I recommend doing on these, once you get your equation, do exactly what I did here. Write down what your steps would be, and then actually think about what the graph would look like. Generally, I see students are very, very comfortable with what we've been doing up to this point. Taking the equation, figuring out what the graph is supposed to look like. Very good at that. Going the opposite direction is a little bit trickier because we're trying to undo all these ideas in our head. And so we can pick out the key elements, like I was doing here. I was picking out all those key elements first, not necessarily in the right order, because that is tricky to try and put everything together in the correct order. Write down all those elements, and then write down the equation you think would do all those things. Once you have that, then go back and check yourself. Think about what the graph would look like.